Okay, so we concluded chapter 2, which was the review of the basics. I'm pretty sure some of the review was basically new to you guys, but we try to go into detail, as much detail as possible, so you guys have a better understanding of what is needed for the propulsion analysis and propulsion design. So, okay. Chapter 3 is the first chapter that talks about the jet engine and the analysis of the jet engine. We are going to have a wholesome view of the jet engine now. And we are going to essentially calculate thrust generated by jet engine. That's the whole goal. That's the main goal of the class, of this chapter. This is a short chapter. The calculations are pretty straightforward, and but they can actually get very complicated as well. So on the surface, they are pretty straightforward and easy to comprehend. But you always have to be mindful that they get complicated very soon. Is there any questions about the chapter 2, about the review, or the problems we solved? No? Okay. So, we will have a little bit of introduction in which we talk about thrust calculation and the main equation we are going to use to calculate thrust. And then we will talk about something called the installed thrust. And you will see the difference between installed and uninstalled thrust, which are going to be the topics of today: introduction and installed thrust, and also thrust calculations using impulse. If we have the time. Then we will move on to rocket thrust and the air breathing engine performance and modern engines. I expect this chapter to be done in 3 lectures. So first 2 lectures, we will essentially go over the equations, go over the material, and for the third lecture, we will solve some example problems. Okay. So the first thing you need to know before jumping into this chapter is to know what is an aircraft engine, or what does it do? Why do we have an engine on an aircraft? To generate thrust, okay? Yeah, is this the only thing that the aircraft is responsible for, or is it the engine can do? Is this the only thing that it that's correct. That's completely true. But our look at the thrust generation is a very macro level view. So we are looking at the forces that are acting on the plane. So aircraft, the main job is to produce thrust. Can aircraft produce any of the other 3 main forces? And what are the other 3 main forces on an aircraft? Lift, drag, and weight, right? So can engine be used to generate any of the other forces? I mean, if you add an engine, it will add to the weight of the aircraft, but it is not the purpose of the engine, right? Adding weight is not the purpose, right? Main purpose is to produce thrust. What else can we use it for? Okay, how would you produce drag? Reverse thrust, exactly. So that's another function that engine can be used for. Okay? Like a rotorcraft. Exactly. So that's actually what I was looking for. I mean, your engine can also reverse drag is completely 100% true. Can also be used to generate lift, right? So essentially, it is thrust, lift, and drag, all 3 of the forces, and also it adds to your weight. So engine does a lot of things. But the main mechanism behind generating thrust or any other form of force is the mass flow rate, right? So we have the jet engines work with the mass flow rate. In the air-breathing jet engines, we are dealing with the air mass flow rate and also the fuel that is being added to your to the air at the combustor or afterburner, depending on the design. We also have other types of jet engines, like the liquid rocket engines. For the liquid rocket engine, you have a fuel and you have an oxidizer. Right? So the oxidizer and fuel are the main things that are responsible for thrust generation. Okay. Can you think of any other type of engines as far as the fuel goes? Like we have the air breathing, we have the liquid fuel, and that are essentially rocket engines, right? That's correct. We have, but they don't work with the mass flow rate, right? You have essentially Hall thrusters, not ion thrusters. That was a good one. What?
Steam engine.
Steam engine. How does the steam engine work though? Okay, well you move a piston with water, right? You don't generate thrust, right? So here we are talking about jet engines, and we are generating thrust based on the flow rate of something, right? We also have solid fuel engines, right? That are mostly used on spacecraft, spaceships. Yeah, and spaceships. I don't know if you can use solid fuel engines on a spaceship that is designed to move into space, because those are very powerful, right? And very inefficient. But you can definitely use the ion thrusters on a spaceship. Okay. So since Josh brought up the ion thrusters, and since I'm very interested in ion thrusters in general, you mentioned it. Yeah, it is basically the same thing, right? I want to give you guys a bonus point here, right? So for online people, I'm just writing bonus point on board. So nothing special. And the bonus point is to give me a report in a week about ion thrusters or Hall thrusters. How do they work? Maximum 2 pages. Not more than that. And I assume some of you already know how they work. How do they generate thrust? What is the main working fluid? I don't know if you can call it fluid, but what is the main working material of an ion thruster? So essentially, you have to answer these 2 questions, and you'll get a bonus point for it. And keep in mind, bonus points are worth half a point of your final grade. Yeah. Pardon me?
I guess the heat transfer data.
Yeah, I mean, they were too much. Actually, if you had aerodynamics with me in the prior years to the heat transfer class, I would give 2 points. Yeah. So.
You're just handing out it.
Huh?
You're just handing out it.
Yeah, exactly. That's what happened. So that's why I changed the policy, right? Yeah. But you cannot change policy at the end of the class. Right? Okay, so let's continue. So bonus point, thank you, Joshua, for bringing this up. you'll get to get a bonus point for it. So let's continue. Let's talk about the regular engines so far. Let's go over this engine we have here and talk about different stages of this engine. What does every number essentially, which we call a station, what are each of these stations? What is each of these stations? Okay, the zero station is essentially unperturbed flight condition, ambient air coming to your engine. Station 1 is the inlet or cowl lid. We are going to use inlet lid in this class. Station 2 is essentially the air intake exit, or the inlet of the compressor. So we have a multi-spool system here, meaning that we have two compressors and two turbines, right? We have a low pressure compressor, high pressure compressor, and then high pressure turbine, low pressure. Okay. So number 2 is the exit inlet of the compressor. Number 2.5 is the exit of low pressure compressor and inlet of your high pressure compressor. Number 3 is the exit of high pressure compressor. What is the next step after the compressors here? What? Fuel. Fuel is not an step. It is not an step, right? It is not a step. Combustor, right? Exactly. So we add the fuel to the combustor, right? So yeah, essentially the inlet of the combustor. Then after the combustor, we have the inlet of the high pressure turbine. Then we have the exit of the high pressure turbine, which is the inlet of the low pressure turbine. And where is it? So part 5 to part 7 are essentially your different stages of afterburners. Actually, we'll talk in a little more detail later on. But is there any one of you guys who knows what do afterburners do?
Just like reignites the hot gases.
Exactly. So essentially you want to provide more thrust by adding a little bit of fluid to the hot air that is coming in after the turbine, and you want to make your system more efficient. But we will talk about this later on. Then at stage 8, we have the throat of the nozzle, and stage 9 is going to be the exit of the jet, right? Again, ambient. But what we want to do, as I mentioned, in this chapter, we want to have an overall look at the engine. So essentially, we are not going to talk about the details, compressors, turbines, combustor at this point, but we just want to talk about the calculation of thrust based on the inlet and the outlet conditions of your jet, right? To do so, we always have to start with choosing a control volume, right? So the easiest choice of control volume is this type of control volume. So the inlet part is very far away from your jet. So essentially the effects of the jet is not going to be seen at the inlet. And the exit part and the outlet part include some parts of the exit of the jet, all of the exit of the jet, and some of the ambient air and pressure. We also have the other part of the control volume far away from the jet walls. Okay, jet engine walls. Is there anyone who can explain to me why are we not choosing the jet engine itself as a control volume? Why are we making it bigger? What is the difference? So to answer this question, you have to be able to answer another question. What is going to change if you change the control volume in general? What is going to change if you change the control volume? Mass flow rate may change. Yes. What else? Pressure. So essentially, what Newton is telling us is that the whole situation may change if you change the control volume. The forces, the pressures acting on your body, the pressure forces acting on your body, and also the mass flow rate itself. Not the mass flow rate, the inclusion of the mass flow rate may change. Not the value of the mass flow rate, but how you include it in your analysis. Okay? So what does it mean? If we have the jet engine at the control volume, then you have to calculate and you have to include the forces that is being applied to the fluid by the walls of the jet, right? So that would have been a little more complicated step, and which we will talk about later on. And then we couldn't have used the inlet, and that would be very complicated as another body of the control. But what we can do is to use this flow stream that is essentially affected by the presence of the jet. Okay? But that has a variable area as well. So it is complicated. We will talk about it later on in this chapter, and today if you have enough time. But the point is you want to choose your control volume to make your problem as simple as possible. Okay, and the other thing that you have to keep in mind is that we are actually neglecting the presence of pylon and the wing, right? So we are just looking at the jet itself. So if you do so, if you want to find the pressure distribution, based on what you see here, the pressure essentially all around the jet, the pressure acting on this control volume must be the same, right? Other than the exit, right? So essentially your pressure distribution will look something like this, right? We have P naught all over and PG at the inlet. We can actually subtract PG by P naught and make it a little even simpler. So the only place where you have pressure force present acting on your body is going to be at the outlet, at the exit of the jet engine. So what this means is that the pressure forces, the integral, the first one, the integral, double integral, the surface integral of pressure forces acting on the body must be equal to 0, okay, for a constant pressure. And we can also use the gradient theorem to convert this surface pressure to a volumetric pressure. Is there anyone who remembers what the gradient theorem was? It was pretty simple. So essentially, use the gradient of a scalar, right? This is your pressure to convert your surface integral to a volumetric integral. So we can actually do that and then make everything simpler. But if you apply this equation of the analysis we have to your main equation, we can get the momentum equation, which we'll go back later. But before finding the final momentum equation, we want to apply the conservation of mass equation. So whatever that is going in is going to go out as well. M dot sigma M dot in is equals to sigma M dot out. But what are the M dots in? Or M dot out. We have M naught, that is the section that is that section of the flow that's going inside the jet, right? And at the outside of the jet, we have already added a field to it, so we are gonna have m naught, m naught dots, m dot naught, whatever, plus m dot f, and we also at the boundaries, we have fluid coming in and going down at the rate of m dot s. Okay, so if you write the conservation of mass equation, this is what you are going to get. Your m dot in is going to be rho naught v naught a, right, which is the area here, plus m dot s plus m dot f, and your m dot out is m dot naught plus m dot f plus rho naught v naught a minus a naught, right? And A9 was section 9, if you recall from the, I should have had the picture here. Yeah. Section 9 was essentially this, the exhaust. Is there any questions so far? So if you simplify things, your conservation of mass is going to look like this. M dot S is going to be equal to M dot naught minus rho naught V naught multiplied by the exhaust area. But the next step is, of course, to apply the momentum equation, the integral form of the momentum equation in the x direction looks like this. Your momentum out in the x direction minus the momentum in the x direction is going to be equal to the summation of forces that is being applied to the fluid in the x direction. Okay. So what are the momentums out? What is the outlet of this control volume in the x direction?
M dot out times velocity.
So m dot out, what is the m dot out? That's m dot naught plus m dot f, right? Times the velocity plus what?
Plus
Okay. Can you repeat what you said? So we essentially at the outlet we have two different sections, right? We have the ambient conditions, right? For which the area is A minus A9, right? So whatever is going out here is rho naught V naught multiplied by that area, A minus A9, right? And we have the m dot naught plus m dot f that is going out at A multiplied by A multiplied by velocity, right? Okay. Is there any questions there? So that is going to be your exit. Okay. Of course, the velocity is then multiplied by the velocity. Yeah. What about the inlets? What about sigma m x inlets? What is coming in to the control volume? What is coming into the control volume? Let's go with someone else. Let's go with China. So what is coming in here? So this portion is just m dot naught, right? But since you have the density and area, and this portion is supposed to be not affected by the inlet, right? So you can have you can look at the whole thing as one whole section of the control volume, right? So you can say this part is rho naught v naught a as the m dot part of it multiplied by the velocity coming. Okay? Is it clear? So what else is coming in? M dot s, that's correct. M dot s multiplied by v naught, right? So that's your whatever coming in. And then what are the sigma of forces that is going to be applied on this? What are the forces that are present here? If you recall, we had the pressure distribution. The idea was that the only part of the system where your pressure is not zero is at the exit, right? For which the pressure was Pg minus P naught, right? Or P9 minus P naught. That's all. Why did I say P9? P9 minus P naught. Okay? Confuse myself. So, what is you have the pressure, how can you calculate the force, the pressure force? Multiplied by the area, that's it. So delta P multiplied by A9, P9 minus P naught multiplied by A9, that is one of the forces acting on it. And that force is actually giving you, based on the Newton's third law, right? We have a fluid force, a fluid reaction force, that must be equal to whatever, not equal, but must be equal to the whole thing. The balance of these and the pressure force over there. Does it make sense? So the forces that are present are a fluid force minus P9 minus delta P multiplied by A9. So if you write that equation, if you just plug in the values, this is what you are going to get. You can simplify it, of course, to get to this equation. So essentially, m dot naught plus m dot f multiplied by v9 minus m dot v, m dot naught, v naught equals to negative f of x of fluid minus delta p multiplied by a0. So this negative sign for this f essentially means that the force is being applied in the other direction, right? Your x is this direction, your positive x is in this direction. Negative f of x means that this force is in this direction, right? So what does a force in this direction remind you of? That's correct. That's correct. But friction is happening inside the duct, right? We are not looking at inside the duct here. And we are looking at this. This is essentially arbitrary control. Drag should act in the other direction, right? Should act in the positive direction. It's pushing your airplane back, right? Thrust, right? So essentially, this f of x of fluid is the thrust you want to calculate, you want to find. Which is then equal to the engine, and your engine force or the thrust force. So if you rewrite the equation, you can find the main equation for thrust calculation, thrust analysis. And thrust is equals to m dot naught, which is the mass flow rate coming into the engine, right? So the inlet mass flow rate plus m dot m is the fluid mass flow rate multiplied by v9, which is the exit velocity. minus m dot naught, again, inlet mass flow rate multiplied by V naught, inlet velocity, multiplied by your delta P, P9 minus P, the exit pressure minus the ambient pressure equivalent, multiplied by the exit area.
Well, I'm trying to get a visual on this. What's happening is air is coming up the engine.
Yes.
And it's getting compressed and shooting out the other way. So it's going to the left. That's what I'm.
It's going to the left? Or who's left? My left or your left?
My left.
Okay, so, no, air is going this way.
Yeah, air is going into the engine. And it is being released of the other end. Fuel.
That's right.
And fuel's coming out again. So it's going forward. That's what's propelling it forward, right? So it's going to my left.
It is going to your left, right?
That's where it would look.
But positive x is to the right.
Positive x is to the right.
So when you have a negative force, as far as the positive x goes, this means that you're pushing your engine in the left direction, the forward.
Why is positive x to the right?
That's just the definition. That's
just how they have it over here?
That's, yeah. You could have it the other way around, then your force would have been positive. So whenever you start working on a problem, the first thing you do is you define your coordinate system, right? That's always the first thing, and that is something you can do. Hopefully in the flight and orbital mechanics course, you will see a lot of coordinate system definitions. But you actually see that in your dynamics and kinematics too, right? Yeah. So, is there any other questions? No? Okay. So, yeah, this shouldn't have been here. But this force analysis, we call this net uninstalled thrust. And we're going to discuss why it is called uninstalled thrust. And we usually use subscript N and also the subscript uninstalled to show the uninstalled thrust. Essentially, it's going to be equal to the same equation we saw before. Okay. So the first term on the right-hand side of this equation accounts for the exhaust momentum through the nozzle. The second term on the right-hand side accounts for the inlet momentum. And the third term on the right-hand side accounts for the pressure area. So, as you can see from this equation, the inlet momentum contributes negatively to the engine thrust. So, which essentially means that it represents a drag term, which is called the ram drag. So, if you wanted to define the ram drag, it is going to be the penalty of bringing air inside the engine with a finite momentum. So the ideal case you want to see is the air coming into your system with a zero momentum. But is that ever going to happen? Right? Of course not, because zero momentum air means that it is not moving, right? So nothing's coming in. And if you recall, although this represents a drag, let me actually make the question. So the proper propeller engine, propeller aircraft, right? The idea was they cannot. The idea is they cannot operate in high altitude. Okay, is there anyone who can tell me why? It is directly related to their engine, right? Exactly. So essentially, your propeller adds momentum to the air, right? That's the job. So essentially, in effect, it is adding ram drag, right? But in higher altitudes, your air momentum is so low that your propeller cannot add enough momentum to your air. So adding momentum to the air at the inlet is actually very important, right? Although it eventually reduces your thrust, but without it, there's no way you can have any thrust, right? Does this make sense? In this type of engine, of course. Okay. So let's talk about the third term here, the pressure area. So as you can see, this essentially is giving us a subtraction of your pressure versus the P naught, right? So if your exit pressure, what will happen if your exit pressure is smaller than the ambient pressure? It is called this situation. When this situation happens, we say the nozzle is overexpanded. So what will happen to your thrust? Or can this happen? What is the situation? What is the condition that this can happen?
There's a supersonic.
Yeah.
So I know if it's overexpanded, then we have to increase the pressure, which that's a shock.
So the goal here is not to get to the sonic condition, right? So we are already talking about the exit pressure, right? Does it make sense? So it is already all of the end, right? And if you remember, we actually had a discussion in the Quaterota at the beginning of that class, in which we say that P0, P naught, P naught is usually equal to P0, right? Unless for a specific cases. You remember the discussion we had? I mean, just the forum here. That's all right, because we are talking about it right now. So, we call it the over expansion. Think about it. What is going to happen? Let's say there is a flow stream coming out, right, or coming into the ambient, whatever, right, with lower pressure. What is going to happen to that flow stream? Like, what will happen if you wanted to visualize it? Let's say you have this exit. It happens in the supersonic jets, of course. Yeah. Let's say you have this inlet coming in. I'm going to delete this later on. And your pressure here is smaller. Let's say you can mark the flow stream, of course, because the pressure is different, right? So the flow stream is going to be different. So what would be the shape of this flow stream? So the pressure is smaller than the ambient pressure. So are we on the same? Do you understand what I'm talking about when I said flow stream? There's a specific flow stream that is coming out of this outlet.
What we saw on the previous.
Yes. That we actually had it for the inlet, right? We didn't have it for the outlet, right?
Wait, so that's the outlet.
We are talking about the P9. Station 9 is the outlet. Okay, that's why I had all the numbers at the beginning. I just want to. So what will happen to the shape of this flow stream? Okay. We have the P9 here, which is smaller than P0, right? Which means that the ambient air is going to exert some force to your flow stream. So your flow stream is going to become denser, right? The area is going to become small. The area that is between the streamlines is going to become small. And that's what you usually see when you look at the engines of supersonic jets, the outlet of the supersonic jets. So, okay, so this happens when you are dealing with the supersonic conditions. And meaning it happens in the convergent divergent nozzles with area ratio larger than what is needed for a perfect expansion. If P9 is equal to P0, your exit pressure is equal to P0, then the nozzle is perfectly expanded, which is the case for all subsonic jets and sometimes in sonic or supersonic jets. So what does this tell you? In all of your subsonic jets, your P9 is going to be equal to P0. The right nozzle ratio will give you that. And if P9 is larger than P0, then the nozzle is under expanded. Which can happen in sonic or supersonic jets only. And it will happen with inadequate nozzle area ratio. Well, what is going to happen to your thrust? Let's say, because this is a design parameter, right? You can design your nozzle or your diffuser or whatever, right, in a way that gives you a lower pressure or higher pressure, right? That is the idea of a nozzle and a diffuser. So, what will happen if your P9 is smaller than P0? This value is going to be negative, right? Which means that you will lose some of the thrust generated by this step, right? What if P9 is larger than P0, P0? Thrust will increase because that's a positive value. But, and for both cases, that's a huge but, right? The changes in P9, will the changes in P9 affect the velocity? P9. Because we are saying that if this case really increases the thrust, let's design everything so this happens. This under expansion happens, so you can increase the thrust, right? That was the idea, right? But then the question becomes, if it was so simple, why isn't everybody doing it, right? Mainly because you cannot conclude with 100% certainty that this eventually will increase thrust, right? But there are a lot of design problems that will come into play, of course. But that velocity, the exit velocity, may be different as well if you design in a way that P9 is larger than P0 compared to the regular design. Does it make sense? So let's move on. We can essentially, based on what we have seen before, we can say thrust is a difference between the nozzle contributions, both momentum and pressure area, and the inlet conditions, the momentum term. So we can have, that's why actually that's the reason we can have this look from the outside of the jet, right? We don't need to talk about compressors and the turbines and everything when we are talking about thrust calculations, because it's just exit and the inlet, right? We call the nozzle contributions the gross thrust. Essentially the only two parts, the exit part, F of G, that's why we call it PG, because F of gross thrust. F of G is M dot naught plus M dot F, V9, plus P9 minus P naught, multiplied by your exit area. And the inlet contribution, as we have seen, is called the ram drag. We can find the ram drag as, we already know how to calculate ram drag. We have seen the equation before. So eventually, we can essentially find the thrust as a subtraction of the gross thrust minus the ram drag. Ideally, your ram drag, you want to decrease the ram drag as much as possible, but as we had the discussion, the presence of ram drag is actually the reason you can generate thrust in the air-breathing jets. And a very important part of this analysis is that you can actually have multiple inlets and multiple outlets when analyzing this thrust for the jets, right? So when you want to calculate the thrust of the jet, you have to include the contributions of all the inlets and all the nozzles. Is there anyone who can give me an example of a jet engine that has multiple inlets and multiple outlets? Let's start with John. What are the different types of jet engines that come to your mind?
I just start thinking about, I know. Well, I think like the SM71 up there, that cone, like, that's funny.
But yeah, that's the variable area, right? The cone content changes the area. Are you talking about the ram jet, right?
Yeah.
All right. Yeah, that's one. So what are the different types of jets? Ram jets, which for whatever reason you guys like so much.
I just started thinking of bypass.
Okay.
Outer section.
Exactly. So the thing is, as I keep mentioning, then in thrust calculations, we don't care about the combustors and the compressors and the turbines. We care about the inlet and outlet. As long as you have an inlet and an outlet, right, you will have thrust generation. It doesn't really matter what is happening there. I mean, what is happening there is going to contribute to the exit condition, of course. But if you have already the end out, you have the exit condition. You can calculate the thrust. So, what are those engines called? Those with the bypass ratio. Turbofans, right? So essentially, when dealing with a turbofan, you are going to have multiple inlets and multiple outlets. Like a regular fan, a regular jet is going to look like this, right? And the exit condition number 9, ambient condition 0. But a turbofan has a fan inlet and a fan outlet. Okay, that's where the sigma comes in, right? And the velocity of the outlet is definitely going to be different, right? Okay, so you can actually do the analysis. This analysis for your and both of these are turbofans. Both of these are turbofans. I thought I have a configuration. One of them is called the front fan configuration, when the fan is in the front, which essentially means that your inlet of the jet engine is going to be has a different velocity, and one of them is fan is in the back. Right?
one is more efficient?
We'll get there. That's actually something that you have to find out later on. Huh? Okay, let's make a guess.
I don't see a lot of
You have the equation. You don't see a lot of aft fan? But is it because of the efficiency though?
might not be.
Okay, and eventually your equations are going to look like this, right? Your general equation for a turbofan for thrust calculation is going to look like this, which we are going to discuss in detail, I think in one of the chapters. We have a lot of chapters in this course. Yeah. So if there's no question, let's finalize the introduction part of this chapter. Let's talk about takeoff. What are the changes to these equations during takeoff? What is going to happen during takeoff that is different from the cruise conditions? Exactly. So essentially, you can safely assume it is not really zero because your airplane is moving, right? But it is so small compared to the exit velocity that you can neglect the inlet drag, right? You can neglect the ram drag because the velocity coming in is so small. Of course, it cannot be zero. It has to have a value, as we have mentioned, but it's so small compared to the exit velocity that you can just neglect it. So for your takeoff thrust, it's essentially just going to look like this. The inlet mass flow, the mass flow coming in or going out, air mass flow essentially, the fuel mass flow multiplied by the exit velocity plus the pressure area contributions is going to give you this. So what is going to happen if you have a perfectly expanded nozzle? What is going to happen to this takeoff equation? The last term will vanish, right? It'll go away. It'll go to zero. So for a perfectly expanded nozzle, your takeoff thrust is essentially going to look like this. And we already know that the fuel mass flow rate is much, much smaller than the air mass flow rate. So the most simplified way to calculate the takeoff thrust is by just finding the exit velocity and finding the air mass flow rate, right? And just multiplying it. If you have a perfectly expanded nozzle, of course. Okay, and it will give you based on this, you will be able to calculate the takeoff thrust. But the question I have for you, and the question is actually a little outside of the scope of this course, but hopefully you know this from your aerodynamics and also lab 1 and all of the design courses. How can we measure the air mass flow rate? Air mass flow rate. And I can't hear you. No, what is the device you use to measure? It is not a mathematical question. Let's say you are a design engineer, right? They tell you that to design an engine for like Colombia. Like
the car, you really have a mass flow rate. You have a device that.
Okay, what is that device on the plane? That's what I'm asking. What is that device on the plane? What? Pitot tube. That's it, right? Essentially, we are talking about the air mass flow rate, and the idea you can safely assume that the air mass flow rate is going to be the same all around the plane, right? When the jet is moving at the same velocity as the plane, as the fuselage or the wings or whatever, right? So the air mass flow rate, you just put a pitot tube there and calculate. That's it. The exit velocity is all, of course, a little. I don't want to say a little more complicated, but you have to have a flow meter at the exit, right, to be able to calculate some sort of flow meter. Okay. Yeah. So let's talk about the installed thrust and some of the issues that we have to keep in mind when dealing with the thrust calculation. So if you had to take a guess, what would be the difference between the uninstalled thrust and the installed thrust? Take a guess. Actually, the difference is in the name. So essentially, when you are no guesses.
Would it be like the engine versus dynamic?
Exactly. Thank you. So when you are dealing with the uninstalled thrust, we are not actually considering the losses that are there because of the aircraft, right? But there are some losses that are going to happen because the engine is connected to something else, right? So that the first part of the class was essentially an engine in isolation, as Tyler said, right? And the installed thrust, when you're talking about the installed thrust, you're essentially bringing in the effects of wings and the pylon and whatever you have on the aircraft, right? So if you want to give a definition, the installed thrust is the actual propulsive force transmitted to the aircraft by the engine, considering all the losses because of the presence of wing and everything else. And the uninstalled thrust is a thrust produced by the engine if it has zero external losses. What are the different sources of thrust loss? Two of the main ones are the nacelle skin friction and the pressure drag, the nacelle pressure drag, and also the second main part of it is the pylon and the engine in installation, which alters the clean drag polar configuration, which essentially means that it introduces a force that is acting in the opposite direction to thrust, and that force is called the interference drag. Essentially, pylons and engines are interfering with the engine operation. Pylon and the installation of the engine, essentially. Whatever you need to install the engine on the wing. So what this means is that this pressure distribution, this very beautiful pressure distribution we had for the uninstalled thrust is not going to happen in the real world, right? The losses are very important, are a very important part of whatever discussion you want to have. And eventually we can simply formulate the installed thrust like this. Installed thrust is going to be equal to the uninstalled thrust minus whatever losses you may have because of the presence of the friction drag on the nozzle, friction and pressure drag on the nozzle, and the pylon engine interference drag, essentially. And you may actually ask, so what is this interference drag? What does it do? I mean, what other than the interference drag, what will the pylon engine installation do? So essentially what is going to happen is that the control volume you have over there is going to be affected by the weights that are generated by the flow under the wing, right, and the pylon, right? So the mass flow coming in is not going to be as smooth as we have assumed, right? Does this make sense? So it is going to affect everything essentially, the comparable, whatever coming in and going out. So let's take a look at your outlet here, which is going to be after the pylon, right? So the weight generated by the pylon is essentially definitely going to be there, right? What we did was that we assumed that the velocity here is v naught, right? And we did calculate the momentum as m and dot rho naught v naught multiplied by the difference of this area by this multiplied by the v naught velocity, right? We cannot do that anymore because the velocity is going to have a distribution, right? This means that your calculations are going to be a little more complicated. Okay. So let's do this. Let's calculate this. Let's take the effects of losses into consideration. Okay. How can we calculate the NASA drag and the pylon drag? Essentially, we have the control volume. These are going to act like pressure forces on the control volume we already have had, and we can essentially do the surface integration, find the momentum, and also the pressure forces. So this part, the first part on the right-hand side, refers to the momentum that is going to be acting on your control volume. And the second part of the right-hand side is essentially going to be your pressure forces. Okay? The reason we cannot do m dot v is because your v is going to change with location, right? Same is true for your density. So we have, instead of just simplifying it to a summation, we have to take the surface integral. And we also have to know the velocity distribution to be able to do that calculation. So if you want to combine this with the uninstalled truss, this left-hand side will give you the installed truss, right? Your final truss. We have the equation for the uninstalled truss. Just have to subtract the right-hand side of the first equation from it, right? The pressure force that is present there because of the weight, right? Or all of the drag forces and everything. Also, the momentum deficit you are going to experience. The momentum deficit you are going to experience because of the weight and the effects of all of the drag forces that are going to be presented in the pressure force. Is there any questions or comments or anything? No. Okay. And yeah, that installed truss by this was this. Okay. So if I were to ask you to find the installed truss on an engine, you essentially have to find the uninstalled truss first, right? And then find the effect of presence of pylon and the wing on your engine, which is going to be a momentum deficit because of the weights, and also the drag forces that are going to be present there because of the reasons we explained, right? And then you have to do the calculations, give me the installed truss, right? Which usually, so you don't usually take the double integral in this course and also in the real world if you were to calculate truss. Let's solve some examples of it, hopefully. Okay. What will happen if you were to change the control volume? Right? The idea was we chose the control volume we had to make everything simpler, right? But if if all of the losses are going to make your life miserable, like this, right? Because this calculation is going to be hard, right? You have to know the distribution, you have to know a lot of things, right? And you don't want to do that. So essentially, this tells us in order to find the installed thrust, it is better to change the control volume, right? But what is going to happen when you change the control volume?
Different mass story.
You will have different. Your calculations are going to be completely different, as we have mentioned. So let's take a look at a different control volume then. Let's say your control volume is essentially the stream. It starts from the point 0, which includes the stream tube that is going inside your jet. Right? And the station 1 is your inlet. Station M is inside your jet, at the walls of jet, essentially, where and F is added, your fluid is added, and you also have the exit at the station 9 again, and F was the negative force that is going to be present there, which is it's a negative, so it means that that force there is thrust, right? That's it. The force itself is the reaction to the thrust, which means that we are going to have the thrust in the other direction. So let's find the pressure distribution here. Okay, the pressure distribution under control volume. The first question you want to ask yourself is that what is going to happen to this stream tube as the area increases? What is going to happen to the pressure of this stream tube as the area, because its area is increasing, right? So what is happening to it? Pressure is increasing as well. That's why you have this kind of distribution for your pressure. The pressure is of course increasing. Then at this point of the inlet, right, at this point of the inlet, I'm talking about these 2 points, right? You essentially are going to have a stagnation point, right? And the main characteristics of a stagnation point is that you are going to experience your maximum pressure. Does this make sense? Okay. And then the pressure distribution on the jet itself, or inside the jet, on the fluid inside the jet, is going to be like this. At some point, you are going to experience your minimum pressure, where your jet is expanded, is at the at some point inside your jet, you are going to experience your minimum pressure, and then you are going to have the exit condition. Okay, so if we were to write the momentum balance equation, you have the outlet condition, you have the inlet condition, right, when they're coming in, and also the sigma of force. So as you can see, the inlet and outlet condition are actually simpler compared to the other one, because we are capturing this stream tube. And if you recall, the flow rate inside and outside of the stream tube is 0, right? So the only place where the flow is coming in and going out is the inlet and the outlet. That's it. But the right-hand side of the equation is going to be a little more complicated, because we have changed the control volume. So we are going to divide each section to different parts. The pressure force from 0 to 1 can be calculated by a double integral, the surface integral of P minus P naught, dAn. The pressure force from 1 to n is going to be calculated by double integral of the surface integral of P minus P naught, BAN, and you have to keep in mind that these P's are changing. So it is not a simple integration. We can actually, we are going to call the combination of these two forces, the subtraction of these two forces actually, we are going to call them the skillet drag. Okay, so let's go back a little bit. Let's take a look at the first part, part 0 to 1 of your control volume here, the section 0 to 1. Okay, let's take a look at it. We have the double integral or the surface integral of P minus P naught DAN, right? Is P larger than P naught here? Yes. Okay. What about dA? Is dA a positive value or a negative value? Positive value, right? Why is dA a positive value? Because the area is increasing, so the changes in area is always a positive value. So what does this mean for your pressure force from 0 to 1? It is always a positive value, right? Okay. Okay, so it is actually, this is called, I should have had this here, but I forgot. This is called, this positive force, this always positive force, is called the pre-entry drag or the additive drag. That is a drag that is going to be added to your thrust. It is not going to decrease your thrust, right? So essentially you have your thrust force here, somewhere here. It has a negative sign here. But I mean, if you do the calculation, I should have had the final calculation here, but that's beyond the point. If you do the math, you will see it yourself. Pretty easy. This pre-entry drag or the added drag is essentially going to help your thrust condition, right? Because it is compared to the other types of drag, it has it is in the other direction compared to the other types of drag. But then the question may become, what will happen if your P is smaller than P naught? So what will happen to that pre-entry drag? It is essentially going to be exactly the same thing, because when your P is smaller than P naught, it means that your area is becoming smaller. So your stream tube starts from a larger area to get to the inlet. So your area is going to become smaller and smaller, and your additive drag is going to always have a positive sign, right? So if you do the calculation eventually, if you plug this in, if you do the calculation, you will see that this 0 to 1 is actually going to contribute to your thrust. So what does it mean? Let's talk about it a little bit before moving on. What does it mean? What is when I say a force is going to contribute to your thrust? What does it mean? Because it is not going to increase the thrust, right? It's just going to contribute to thrust. It's going to be added to thrust. So essentially, maybe my question is a little confusing. Let me answer it myself. So essentially, the answer to the question is that it is going to remove some load from the engine. So your engine can actually produce a smaller amount of thrust, right? To get the same conclusion without the additive drag. Does that make sense? Yes?
Said there was a way to avoid the double interval.
Pardon me?
Said there was a way to avoid the double interval. What was that way?
We'll get there. We'll get there in the examples. Okay? But essentially, we'll get them. Okay. So if you plug the values in, and we actually, all of the losses that you want to calculate, also the friction drag, all of those, the wall friction drag and everything else, your main equation with that control volume is going to look like this. The part 1 refers to this as spillage drag. Part 2 is the pressure drag on the nozzle aft, or the boat tail pressure drag. Part 3 is the nozzle viscous drag. Part 4 is the pylon drag. Part 5 is the reaction to the installed thrust force and pylon drag acting on the fluid. Part 6, right, is the pressure thrust due to the imperfect nozzle expansion that which we already have seen. Terms 1, 2, and 3 are the propulsion system installation drag losses. Term 4 is going to account for in the aircraft drag polar, and term 5 and 6 combined with all of the other terms essentially produce the uninstalled thrust. Is there any questions so far? I guess that's it for today. We actually ended up on time. That's the first for me. But yeah.